Yeah, so a little bit about me. I'm Ben, and I'm currently a staff engineer at Aleph Alpha. And basically today I'm going to share a little bit about what my team has been working on for the last 9 months or so as we've been building this out. To start with, let's start with the problem we're actually trying to solve. So, because probably the problem is not a serverless runtime. So, first, our product at Aleph Alpha, we're building Faria AI, and this is this full stack solution for basically enterprises and governments to connect AI into their organization. They usually want to run it on premise in their own data center. And so we're trying to build out everything they would need to do that, especially if they're not primarily an AI company. Now, this is a big scope. There's a lot in this product, but that also means there's a lot of personas. So, but my team is focused on one of them, and that is the AI engineer. So eventually someone needs to get a business problem and then try and use AI somehow to actually solve that. And they are usually trying to get something working, to define the problem, figure out how to solve it, and then get their POC running and get it into production. And these, like an AI engineer is concerned with things like LLMs, prompts, chunking strategies, vector databases, these sorts of things. And that's what they really want to spend all their time doing, because this is how they know to solve the problem. So their typical workflow looks something like this. I'm simplifying a bit, but they have a problem now. They want to maybe define a data set. And this probably has some example inputs, like example scenarios of what the problem is, maybe some expected outputs, or at least a way to grade the outputs so they can guess, did it do it correctly or not? And then they start working on the problem. They iterate on some methodology. They then use the data set to evaluate, did this work? How badly did it not work? Oh, let me try again. And this loop kind of happens again and again. And then eventually they find something that's working, and they deploy this. They monitor it based off user feedback. They funnel this back into their data set and start over. Now, this works, but there's a few issues that we run into. One, this phase usually isn't happening in production. It's often on a dev node or on a laptop somewhere, and so they're not always, some people figure this out, but they're not always evaluating the thing in production, because sometimes that's a little hard. And then when they need to deploy, the AI engineer needs to build a container, deploy it to Kubernetes. This isn't usually the stuff they want to focus on. They want to play with the LLMs. So, and also because there's just a lot of friction in this process, if they're lucky, they can get it done in one day, but this kind of stretches out and stretches out. So with this situation, we asked ourselves, how can we help AI engineers iterate on and evaluate their ideas faster in production? As you all know, as you're maybe writing tests first and then writing your code, the faster that feedback cycle is, the faster you can learn what you don't know about the problem so that you can find a solution. And can we help these engineers do the same thing? Can we get, this isn't the best diagram, but can we get something like this where it's just much faster, that I can deploy a new version, test it out, compare multiple versions together, update my data set, and that this is something that's happening as an ongoing basis? So our team, we call ourselves the Safari kernel, and we're trying to provide this focused environment for AI engineers to develop and deploy AI methodology. And this focus is a big part. Can we help them actually focus on the problem at hand and spend most of their time being productive at solving the problem and not worrying about all the other complexity of making it run? So to do that, this is where we landed. And I'm going to walk through the different aspects of this. So first, let's talk about serverless. So as I said, in order to provide focus, we need to remove some complexity. And this is where the kind of serverless philosophy helps a bit, because the whole idea is that ideally you're removing some of the accidental complexity. There's some fun papers on accidental versus essential complexity. The idea is I want to focus more on the essential complexity of my problem. What is the actual business problem we have, and how am I going to solve it? And I should spend most of my mental energy on that. And can we as a platform take more and more of the complexity of how this actually runs and gets deployed and all of this away from them? When you're deploying something, a container kind of looks like this. You have to not just ship your AI logic, but maybe have a framework that you're using that helps you use it. Then you need to probably accept a web request, and now you have an HTTP server, and then you also need like the whole OS. This is a lot of stuff, and ultimately, this is, if you're shipping this into production, this is all your responsibility. You obviously are pulling this in, you're not building it all yourself, but it's still your responsibility, what you choose here, what you put in there, and what's actually running. And so this serverless mindset is like trying to, can we take away some of this stuff at least? Can we help you focus more on just processing a single event? So then your code becomes a lot simpler because you're not thinking about like, oh, I need to handle multiple requests at once. Just, okay, I have one request. How do I process this? And the serverless platform kind of takes care of all the complexity of doing multiple concurrent requests at once, what OS to choose, maybe even what server to choose. So this felt like a natural fit. Like this seems like this is kind of the direction we want to go. It's helping pull some of the complexity out. Now, how does WebAssembly fit into this? We now want, we seem to want to take some custom user code and run it for the user. We just said we want to take on like the OS and the HTTP server. So somehow they're going to give us some code and we're going to run it for them. Well, this is not an easy thing. So maybe WebAssembly can help us out here. And what we leaned into is at the beginning of last year, the WebAssembly Component Model stabilized. And this allows you to run WebAssembly not in the browser, but maybe like in a server context. I mean, you can also run components in the browser, but maybe I want to like actually just take some code and define how it's going to run. And how it does this is you have these things called WebAssembly interface types. And here you can kind of define, you're gonna compile your WebAssembly component, and it's gonna have some imports, some things that it expects to be able to link against to call. It's also gonna have some exports, things that I as a host know that I can call. These are functions you export. So you kind of get this very strongly typed ABI, kind of FFI type thing. And it's kind of not too dissimilar from Rust. You have like types like results and options. You have like enums with data. So this is really cool. And you basically get to define like for this component, what is its OS? What does it have available to call? And the most popular version of this is WASI, WebAssembly System Interface, where they define all of the system interface calls you would have with the same language, but you can also define your own. It also works with Python, which is very important for us. AI engineers really like Python, so we're probably not going to convince them to write Rust. So can we let them still write their code in Python and run it? And then because we like Rust, well, we want to also write some of this AI logic in Rust, so we make sure that works, but we could also expand to JavaScript or Go or whatever else compiles to the component model, which is really cool. The host doesn't care what language it's written in, just that it meets this contract. WebAssembly also, like we're running custom user code, we also get like capability-based security built in, so we don't have to do all the sandboxing stuff. Wasmtime does all this for us. But we can define, hey, I want this one to be able to access the internet, or have this environment variable, or maybe have access to these files. By default, it gets none of them. So we can really kind of, no matter what code is in there, we don't have to know what the code is. We know what the blast radius is. What could it possibly do with the outside world? Because we can choose what that is. This also lets us define versioning. So we can do a new version. We can annotate when things got added, which the linker decides like what it should actually expose to the component. And when we load the WebAssembly component bytes, we can actually like read the bytes and see exactly which interface this thing was compiled against, which is great for running older versions of the software, backwards compatibility, so that way if someone deployed something 6 months ago, but we came up with a great realization, we need to introduce some breaking changes or add new features, it's fine. The old stuff can still work. We have a code path for that version, and then for the new version, we can go off and add a bunch of new stuff. So this is really cool as well. And there's also an OCI artifact spec for how to package WebAssembly modules in an OCI artifact, which means our users can just push these up to an OCI registry, and then we get all the benefits of storing them, tagging them, checking if like the digest behind a tag has changed, pulling them down at runtime, which is what we do. We kind of just pull them on demand. We can have some dynamic configuration of what should be deployed. We can pull it from the registry. And so this is also really cool. Like we don't have to solve that problem. And if what you want to do is like have a bunch of HTTP-like handlers, there's some really cool WebAssembly serverless runtimes in Rust that you should definitely check out, and you can get all of this. Like, you can just do this. You get all of these benefits I just said. But since we're doing AI, we kind of felt in the previous diagram, there's still this framework layer. There's probably more that we can still take some complexity away that we don't have to give. And so we thought, maybe we can keep pushing this further. Now, yeah, basically there's a bunch of complexity with how to handle models, like stuff like tokenization, when to do retries, what retries are okay, how many can you do concurrently based off of maybe your inference backend, which inference backend to use, because maybe one's cheaper, but it's quantized, lots of things. Sometimes the AI engineers care about these, sometimes they really don't. They just want it to work. And so you can do a lot of this with SDKs and clients, and you can like make some nice libraries of how to do this, and you can capture all this domain knowledge and give it to the user. And we tried this multiple times. We have a few different iterations, some public, some not, of like attempts we've tried at like handling this, but ultimately we're back to the original problem. What it still felt like was, okay, we have a new version, maybe it solves some more problems, but it's still, they have to update it, they have to redeploy their stuff. And ultimately, the ownership of the complexity is still lying with them. We're helping them manage it, but we're not alleviating it. So we're not necessarily taking it away, we're just helping them deal with it. So what if we could? And then the thought was, well, what if we turn this around? What if we stop thinking about the things that they deploy as services, where we're giving them code to run inside their service? What if all we asked of them was to give us the AI logic? What if we view this more as a plugin that plugs into our application that takes care of all the complexity of how you need to interact with LLMs, how you have those things talk to the outside world, and all of the stuff around that. And what we call these things is a skill. So this is like an AI skill that I'm deploying. And basically all we're saying is, hey, you give us the AI logic, you get to write it in Python, and then this links against our host runtime, and we can handle all of the complexity. So we have to give this thing an interface with the WIT types. And what we call this is the cognitive system interface because, well, AI thinking we need a name here. So if you see something in the slides with CSI, that's what this stands for. And this is basically whatever we define as the CSI is the functionality that we provide the AI engineers to call from their code. And when you define this, Wasmtime and WIT bindgen give you lots of cool bindgen for how to generate this stuff. And it allows you to link in Wasmtime your own custom functionality. So when it says that they import something like a chat call, you need to somehow define that. You can give it to Wasmtime, and Wasmtime takes care of hooking that up to your component. But because there's two interfaces, it also allows us to provide a different interface to the skills than actually what we implement on the host. And this separation allows us to remove a lot of complexity for the user. So if I give one example, here we have a chat message. Someone wants to chat with the model. From the skill side, from the guest side, they just express that they want to do a request, or maybe multiple of them. But on the host side, well, of course, this is going to be in an inference. Maybe this is a remote inference. We need something like a token. We might need to check if you have permissions to this model, because maybe it's a special fine-tuned model that only certain people should have access to. But that's something we can handle on the host. So we can take care of, maybe we pull it from the environment, maybe we pull it from the request and dynamically switch. But this is all on our responsibility to handle, should this request go through? And from the skill developer, in their imaginary world, there's no such thing as permissions or authentication. They don't have to worry about it. And on the return side, we also just return to them chat responses. On our side, well, okay, we're going over the network. Something bad could happen. Maybe the network doesn't actually work for some reason. If it's recoverable, we can retry for them and eventually send them their response. Maybe it's unrecoverable. We can handle that, give an error to the user who prompted this plugin, and then we just suspend the execution of the plugin. Well, okay, this isn't going to work. Let's just kill you, and we'll handle it from here. So again, most of these errors just never show up. So if I show you a version of this, which is a very simple haiku skill, it writes a haiku poem. You can see no authentication. Well, it's Python code, so it's a bit hard to tell if there's an error, so I'll switch to the Rust one. What you'll see here is that there's no unwrap, no expect, no question mark. From the person writing this code can never fail. And the reason why it can never fail is because the error will actually never propagate into their code. We handle it on the outside and just stop it if it's an error we can't handle. And so, again, I get to write my code as if these things never happen. And ultimately, we are applying a lot of constraints. First of all, you're doing Python in WebAssembly, which means you can't do certain things. It's still an evolving process of how to do Python in WebAssembly. We currently don't allow it to do arbitrary requests or access environment, and maybe you really want to do this. But because we apply these constraints, we can provide a lot of value because we know exactly what interactions this thing is allowed to do. And because we know what these interactions are, we can basically handle it. Know, hey, in this case, we will need to handle it this way or this other way. And this means we can also evolve our understanding of how these errors or these interactions should be handled and improve it on the host without the user needing to update or redeploy their code. It just keeps working. It makes their code much more portable. If we want to change how we're handling getting tokens, their code doesn't need to update. And we can also add extra features like automated tracing based off all these CSI calls or extra logging. Again, we can do it on the skills that they first deployed 6 months ago or the new ones today. Maybe they get more logs or something because there's more interactions, or they can do custom ones, but we can still provide backwards compatibility, backwards features to existing skills. And basically, going through this process, it really opened my eyes to a new way to approach how we allow users to extend their applications. We can give them maybe a template or some configuration values. But what if we could actually let them use a real programming language, give them access to core parts of our system, and robustly run them without worrying about what could happen? If we could actually control how that code was run, we could actually give them access to parts of our system and allow them to extend it, to come up with new ways to use it, and we're able to provide them a lot of value in that sense. So I think this plugin model, can expand to lots of other applications, and I think it's a super exciting way to think about maybe you know really well how to interact with a certain system, but you want to let your users still define how those things are used. And I think this model is super helpful. And the results were actually really, really cool. We had a version of a summarization that in the previous SDK, the whole summarization was spread over 10 files because of how you had to hook all this stuff up. And by taking the same methodology and rewriting it in this new way, it was able to go down to a few dozen lines of code, which provided a lot of clarity. There's a lot of cohesion because a lot of the decisions at the top matter down at the bottom. You kind of need to know how this thing flows. And this, I wouldn't even say this is the best summarization. And once people saw this in one place, I can tell you every single person who saw this was like, hey, why are you doing it that way? Why don't we change this or that? Or now I have an idea, let's try this. And so by being able to put all these decisions in one place, people were actually able to understand what was happening and improve it. And the speed, we achieved this. We're able to do hackathons now with new users, and they're able to sit down with just add a decorator to a function, import the SDK, and then they can build and deploy and have it running in prod in just a few minutes. And obviously, it's not the most sophisticated thing, but the fact that it's already deployed means that they can edit it, publish it again, and now the new one's running. And so now their iteration cycle of actually deploying their new logic, and now they can eval it exactly how it will run in production, because they can just hit our endpoint and run it there when they do their eval code and no longer have to do it on their laptop. So this is really, really cool, and it makes a lot of these AI engineers very excited because they get to write the code they really care about and not have to worry about all this other stuff. So, like I said, I hope that this talk somewhat inspires you to think about maybe there are ways in which your domain, you have a lot of domain expertise, but you don't know every single use case that's out there. And there might be ways where you can allow users to configure and extend your system. And this is just really, really cool. Now, I said building in Rust. This is a Rust conference. And I can honestly say that I think we built a lot. This thing is like running in production. We're deploying lots of things in there, and we did it in less than a year. And I don't think we could have done this without Rust. I think we have a lot of guarantees from this whole system that we wouldn't get in any other language. And also there's like a bunch of crates, this is not even all of them, that help us achieve this, right? And like we don't have to figure out how to run WebAssembly. Wasmtime does that, and they do it really, really well. We don't have to figure out how to do async or a web server. We can use Axum for that. And we get like cool channels and actor models and all this stuff. Like Marcus on the team can give another talk about our architecture, but there's just so much that we get here. And I just want to say thank you to the Rust community, because there's so many great libraries that we get to use and stand on the shoulders of giants to build something like this and really focus on our problem and to get to leverage all of the cool work that everyone's been doing. So I hope I've inspired you to take a look at what's possible for you. And if you really like what I just said, we're also hiring. So if you want to join this team, we're hiring for this team. If you want to help us build it, we also have other positions if you want to join Aleph Alpha in general. But yeah, anyway, that's it.